Let's talk about solving a second order linear constant coefficient non-homogeneous dE. So the first thing I need to do is solve the homogeneous, which is a y double prime plus 4y is equal to 0. So my characteristic is r squared plus 4 is equal to 0, which gives me r values of plus or minus 2i, which means the solution to my associated homogeneous is c1 cosine of 2x plus c2 sine of 2x. Okay. Now I'm going to make an educated guess for what my particular solution should look like. And again, I have to watch out for if my guess to the particular is in the homogeneous already. Now, the right-hand side, this non-homogeneous part over here, looks like a second-degree polynomial times an exponential. So my guess is going to be that exponential, so e to the x, times a generic second order, which is ax squared plus bx plus c. Now, if any part of this is already part of the homogeneous, then I'm going to need to tack on another x. If that is still part of the homogeneous, then I'm going to need to tack on another x. And since my homogeneous is cosines and sines, none of my guess for the particular is involved in the homogeneous. So this is going to be my guess. So what I'm going to need to do is differentiate it twice so I can then plug it into my dE. So the first derivative is going to be e to the x times ax squared plus bx plus c plus e to the x times 2ax plus b. And then my second derivative is going to be e to the x times ax squared plus bx plus c. I'll pick up an e to the x times 2ax plus b from the first. I'm going to pick up another one of those from differentiating the second. So when I'm done, I'm going to have two of them total. So 2e to the x times 2ax plus b. And then the last part of the product rule in that second one is e to the x times 2a. Okay, so my dE, left-hand side, look like the second derivative plus 4 times the original is going to look like the following. Well, let me factor out the e to the x on all these because they all have e to the x. So if I factor out the e to the x from everything, what's left on the second derivative is an ax squared plus bx plus c plus a 4ax plus 2b plus 2a. That's all from the second derivative, plus 4 times the original, and the original, once I factor out that e to the x, all you have is ax squared plus bx plus c. Okay, so that's what I get when I plug it in. So I'm going to be looking for things that have, let's see, e to the x on them, but then I'll have things attached to x squared. Looks like here's an x squared, and there's an x squared, so an a from here, a 4a from there. I think I have 5x squareds total. Plus, let's see, how about things with an x? That has an x, that has an x, and that has an x. So I'm going to have 4a plus, looks like I have a b and another 4b. That sounds like a 5b. That's all times x. And then what else do I have? Here's a constant. Constant. Woohoo! That was a long line. Constant, constant, constant. So let's see, what are the constants that are a? I got a 2a from there. I think those are the only ones I see, so plus 2a. And then the b's, looks like I got a 2b. And then the c's, I get a c there, and then a 4c there, so I think I got 5c when I'm all said and done. Okay, this should be equal to what I would like it to have on the right-hand side is 5x squared times e to the x. So what this means is I should have 5 is equal to 5. That's true. Was I missing an a on that? I was missing an a on this, wasn't I? Sorry guys, let me squeak that in there. Right? Because this had come from ax squared plus a 4ax squared, so that gave me 5ax squared. So I should have 5a is equal to 5. I should have a 4a plus 5b is equal to 0, because I don't have any x term right here. And I should also have 2a plus 2b plus 5c is equal to 0. What that tells me on this one is a is equal to 1, which if a is equal to 1, then that means 5b is equal to -4, so b is a -4/5. And then let's see, my c over here, if I plug in a is equal to 1, I get 2, and then b is -4/5, so I'll get a -8/5 plus 5c is equal to 0. So this is a 10/5 minus 8/5, that's 2/5. So 5c is equal to a -2/5, so c is equal to -2 25ths. That 2 got really excited, didn't it? Okay, so my guess again, it's way if you scroll up, but my guess again was that e to the x times a x squared plus bx plus c, and I figured out an a, a b, and a c that made it work. So I'll have a 1x squared plus bx, which is a -4/5 x, and then a plus c, and a c was a -2 25ths. So that's my particular. If you add that to the homogeneous, what that means in general is my solution is equal to, my homogeneous was c1 cosine of 2x plus c2 sine of 2x plus then my particular, which looks like a e to the x times x squared minus 4/5 x minus 2 25ths. So that's when you take the guess approach. Again, look at what your homogeneous looks like and tack on extra coefficients if needed. Now let's tackle this problem again using our variation of parameters approach. The homogeneous part is still all the same, so I won't go through that again. I'm just going to focus on the particular here. So my guess on this one is, well, I have some exponential, and let's just say it's an exponential times some function u, which is a function of x, and let's see what happens. So if I take its derivative, it's going to give me a u prime e to the x plus u e to the x. My second derivative will be a u double prime e to the x. I'll get a u prime e to the x from the first and a u prime e to the x from the second, so I have 2 u prime e to the x, and then the last part will be a u e to the x. If you plug those into the left side of the dE, and I'll factor out the e to the x, you get the following. So e to the x times, second derivative is u double prime plus 2u prime plus u, and then 4 times the particular guess, which again, factoring out e to the x, you just have 4u. Combine like terms, this means e to the x times u double prime plus 2u prime plus 5u better be equal to what I want, and again, the right-hand side of my dE, that non-homogeneous part, is 5x squared times e to the x. Well, now both sides have e to the x, and so I'll divide both sides by e to the x. E to the x is never 0, so I don't have to worry about that. And what I'm then left with is a new dE, which looks like u double prime plus 2u prime plus 5u is equal to 5x squared. Well, that's also second order linear constant coefficient non-homogeneous dE. The thing about this one is I've now gotten rid of the e to the x, so this has become an easier problem. So my guess is u is probably some ax squared plus bx plus c. So if I'm going to plug that in, I'm going to need my derivative, which is 2ax plus b, and my second derivative is going to look like, you can write, there you go, 2a. So if I plug that into this dE right here, I'm going to get a 2a plus 2 times the first derivative, which is 2ax plus b, plus 5 times u, which is ax squared, plus bx plus c. So if I combine like terms, it looks like I have, well, the only x squared it looks like I got is a 5ax squared. That came from here. And then for x's, it looks like I have a 4a from here, plus a 5b, which came from here. And then my constants, looks like I have a 2a from the front, plus I'm going to get 2b, it's right here, and plus 5c. This should be 5x squared. Okay, if those two are the same, that means 5a better be 5, and a 4a plus 5b better be 0, and a 2a plus 2b plus 5c also better be 0. And you'll notice here, if you go back in the video, that this is the exact same system that I got before. So I already know if I solve this, just to save us a little time, again, go back up in the video. That means a is 1, b is negative 4/5, and c is negative 2/25. What that means is u, again, was ax squared plus bx plus c, which means I have a 1x squared minus a 4/5 x minus 2/25. My guess for the particular had been u times e to the x. So I now have x squared minus 4/5 x minus 2/25 all times e to the x is my particular, which you'll notice is the exact same solution as I got last time. The powerful thing about this variation of parameters approach is it just simplifies the differentiation down quite a bit, and the systems that you have to solve sometimes come out a little easier, sometimes not, but the differentiation, the plugging in, is quite a bit easier. So one more example, separate one, and the only one I'm going to do at this time is the variation of parameters approach. So y double prime minus 4y prime plus 3y is equal to e to the 3x times a 12x squared plus 8x plus 6. So if I solve my homogeneous, the characteristic is r squared minus 4r plus 3 is equal to 0. And how's r minus 3 times r minus 1 sounding? Which means my r values are 3 and 1. So my homogeneous is going to be c1 e to the 3x plus c2 e to the x. Now, if I were taking a guessing approach for the particular, you'll notice that e to the 3x is part of the homogeneous. So you would have to tack on an extra x. So you'd have an extra x times e to the 3x times a generic second degree. That will be a lot of work. I don't want to do it that way, so I'm going to go with some function u times e to the 3x. So if that's the case, that's our guess. The derivative of that is u prime e to the 3x plus 3u e to the 3x. The second derivative is u double prime e to the 3x. I'll get a 3u prime e to the 3x from here. Same with a 3u prime e to the 3x from there. So I have 6u prime e to the 3x plus a 9u e to the 3x. If I plug that in to the left side of the DE was the second derivative, minus 4 times the first derivative, plus 3 times my original guess. So I'm going to get, if I factor out that e to the 3x, I'm going to end up with a u double prime plus 6u prime plus 9u minus 4 times u prime plus 3u plus 3 times u. So if I start combining like terms, I got an e to the 3x, and I think I only have a single u double prime from there. If I start tracking down my primes, I got a plus 6u prime and a minus 4u prime, so that's a total of plus 2u prime. And then let's see, I got a plus 9u, minus 12u, plus 3u. Well, that's 9 plus 3 is 12 minus 12. I don't think that's any of them anymore, right? They'll go away. Yeah. Cool. This should be equal to, right-hand side of the DE was e to the 3x times 12x squared plus 8x plus 6. Again, you can see that the e to the 3x's, you can divide both sides by that. They're never equal to 0, so I end up with u double prime plus 2u prime is equal to 12x squared plus 8x plus 6. Well, here's the thing, is my first thought is, well, what if I just go with u is equal to ax squared plus bx plus c? That's my first guess, because the right-hand side is just a generic second-order polynomial. The problem is there is no u on this side. So if I start taking the derivative now, the first derivative would only have an x, and the second derivative would only have constants. So there would be no way to get a 12x squared. So I'm essentially going to bump up the degree of this polynomial by 1 by essentially tacking on another x. So I'm going to have ax cubed plus bx squared plus cx. So that means my u prime is a 3ax squared plus a 2bx plus c, and my u double prime is a 6ax plus 2b. All right, now plugging this into u double prime plus 2u prime, I get 6ax plus 2b plus 2 times 3ax squared plus 2bx plus c. So overall, looks like I only have 6a x squared. That was from here. This gives a 3. And then how many x's do I have? It looks like I have a 6a plus 4b times x. That came from here and here. And then for the constants, I have a 2b plus 2c. So this means I want this to be equal to, what was it again? What's the right-hand side? Let me see. Oh, there it is. I want that to be a 12x squared plus 8x plus 6. What that means is my 6a better be 12. My 6a plus 4b is equal to 8. And my 2b plus 2c should be 6. Okay, what that means, I'll let you guys solve this separately, but a is 2, b is -1, and c is 4. Again, take some time to actually figure that out, but that's what I get. So, this was for u. u was ax cubed plus bx squared plus cx. So that means I have a 2x cubed minus x squared plus 4x, and my particular guess had been u e to the 3x. So I get a 2x cubed minus x squared plus 4x times e to the 3x. So my overall solution is y is equal to the homogeneous we did a long time ago, was c1 e to the, I can't remember if I had x or 3x first. I think I had the 3x first. Doesn't really matter. Just trying to stay consistent. So c1 e to the 3x plus c2 e to the x plus my particular, which if I kind of write this a little different, just to prove a point here, they all have an x in common. There's a e to the 3x, and then there's a 2x squared minus x plus 4. So you can see if I had gone with the guess approach, here's that generic second degree polynomial, here's the e to the 3x, and there's that extra x kicker because I had e to the 3x was part of the homogeneous.